Hello, thank you for listening to my talk. I'm Tahmid, the third year PhD student at UC Berkeley at the Berkeley Power and Energy Center. I would like to thank the Hearts to Humanity Eternal Fellowship for helping support me as a PhD student. I'm excited to share with you this talk about the design and implementation of an 8-level flying capacitor multi-level boost converter for high voltage power distribution in electric. This is a particular research project I worked with over the last year that ties in much of the research in flying capacitor multi-level converters that our research group specializes in and demonstrates so in a high-performance practical application. Listed here are a few of my collaborators for the project, Dennis, who is a graduate student in our lab, as well as Rahul and Logan, who have since graduated. Our research advisor is Dr. Robert Pulawa-Pitkursky. I will start by discussing the background and motivation for the project, how the FCML converter is an excellent candidate for this application, how it is designed along with the startup circuitry. We will look at the design hardware prototype and the experimental results towards the end of the presentation. Transportation, including air travel, accounts for a large proportion of US greenhouse gas emissions, and this is expected to only continue growing. As a way to address this concern, battery electric automobiles have gained popularity in recent years. And aviation has also been seeing a shift towards more electric propulsion systems. More electric aircraft are also of interest for reducing long-term operational and maintenance costs for short-haul flights in the future. Lightweight onboard DC-DC converters play a crucial role in this transition. Electrification of flight requires efficient, lightweight, compact, and reliable power conversion. And today I will focus on the design of one such DC-DC boost conversion system. When considering the electric powertrain design in more electric aircraft, there are several possible options. For example, we could have an all-electric system with a battery or fuel cell going through the power conversion stages, driving the motor. We could also have hybrid electric powertrain. For example, a so-called series hybrid electric powertrain where a motor is driven from an inverter that is powered by the battery or from combustion or both. We could have a parallel hybrid electric powertrain where the combustion powertrain also drives the motor parallel with the electric drive system. All of these schemes, regardless of the implementation, boil down to a general setup that consists of a battery powering a DC-DC converter, which feeds a DC-AC inverter, which then drives an electric. And the focus on the work being presented here is the DC-DC converter itself. I will talk about that converter within the system, and then we will look at how it is implemented in this project. To motivate the DC-DC converter in this application space, let's start by looking at the aircraft high voltage bus architecture. The inverter is driven directly here from a high voltage battery. And as you may anticipate, increasing the DC bus voltage results in reduced cable losses. However, this places increased demands on the system insulation. Notably, not just the cabling, but also within the battery pack and module itself. We will get around this and reduce this stress by adding a DC-DC converter, which we will look at in a little bit. So the battery side voltage here shown is at high voltage, which necessitates robust insulation within the battery pack. At high altitudes, this becomes even more crucial. Paschen's law can be used to approximate the safe operating voltage for a given separation. The required separation for a given operating voltage is also subject to the inclusion of suitable safety factors to account for manufacturing tolerances, movements during vibration, and so on. With the 1 millimeter gap distance as shown here, the air breakdown voltage at sea level is around 5.5 kilovolts. However, at 50,000 feet altitude, we see that this drops down to about 1.1 kilovolts, a significant factor of 5. So high voltage operation at high altitudes demands robust insulation, which contributes to overall system mass. Now, if we add in this DC-DC converter, what we're able to do is utilize a lower voltage battery pack, which significantly reduces the insulation requirements within the battery module itself. Of course, that assumes that the DC-DC converter is sufficiently lightweight, which is the goal of the project. So what is considered sufficiently light? Now, that value would depend very particularly on the specific battery chemistry, voltage, and integration into a particular aircraft platform. So to decouple the target from the particular platform, it is perhaps more useful to look at specific power projections, for example, from this NASA-funded study. Using historical data and a logistic projection model, multiple different projections are derived for aircraft onboard power converters, which also lumps in DC-DC converters. Here I can show two cases, one, a more aggressive projection along with a more conservative one. Now, these 2050 figures of roughly 50 kilowatts per kilogram and 25 kilowatts per kilogram serve as useful reference target when designing this converter. Each of these individual converters can then be placed in a larger system where they operate in parallel to increase the overall power handling capability of the system. This modular approach is also beneficial for continued operation if a particular converter goes down. We have already seen how a boost conversion stage can help reduce insulation mass. This particular scheme also allows the use of various batteries, cell chemistries, or alternative sources such as fuel cells. It can even enable a distributed battery placement architecture within the aircraft. Finally, having this converter allows for regulating the DC bus itself and handle the varying voltages associated with battery charging and discharging cycles. This can also have a marked improvement in the overall system efficiency since the inverter efficiency can have a dependence on the input voltage. In this example inverter at 5 kilowatts, dropping from 1 kilovolts at the bus voltage to 600 volts drops the efficiency by about 0.65 percentage points. And at 5 kilowatts, that corresponds to 30 watts of loss. And for larger systems, we can imagine that this would correspond to even greater system losses. While the full system may contain multiple batteries and power converters, the scope of this work is a singular DC-DC converter. We will consider a battery voltage in the range of 500 volts to 786 volts, a specification that we have received from our industry partner, and an output voltage of 1 kilovolt with output power at 10 kilowatts. This DC-DC converter is based on the flying capacitor multi-level converter. Let's now take a quick detour and look at some device trends. First, if we look at passive volume components, for example, here in this AC-DC wall charging application, we see often that the volume of the converters is dominated by the passive components, notably the magnetic components, so transformers and inductors. Existing research has shown that capacitors tend to have much higher energy densities, and the best capacitors are over 1,000 times more energy dense, which suggests that we want to use topologies favoring capacitors to transfer energy. We will come back to this point in a little bit. We can also look at trends in energy loss associated with particular devices. And we can look at the figure of merit, which is a metric that tells us the loss associated with each of these switches. The figure of merit is shown here for silicon and gallium nitride switches, and a higher figure of merit corresponds to a better performing device, which indicates reduced losses. And we see here that the figure of merit is better at lower voltages, regardless of the technology, whether that be silicon or gallium nitride. So we're looking here at the figure of merit for a single switch, but what happens if we series connect N switches? We get an improvement in the figure of merit itself, and we see that what this points to is we want to use topologies with many low voltage switches in series rather than a singular high voltage switch. So combining these points, the multi-level topology is an attractive alternative to standard two-level converters because they do enable the utilization of devices with lower blocking voltages and correspondingly higher figures. Here is a schematic of an 8-level flying capacitor multi-level converter that is used in this work. There are 7 switching cells, each comprising 2 complementary switches and 6 flying capacitors. For this converter, if we boost V in, which is shown on the right, to a higher voltage V out, shown on the left, which is 1,000 volts in this application, the blocking voltage for each transistor is about 143 volts. As such, we can use 200-volt devices while maintaining headroom for voltage level and switching overshoot. If we consider the figure of merit of on resistance multiplied by COSS, which we looked at in the previous slide, we know that the lower blocking voltage devices in the multi-level converter perform better than higher voltage switches in the two-level converter. And this indicates that extreme improvements in efficiency can be obtained by a multi-level design in this kilovolt scale application. The FCML topology also offers a number of additional performance benefits, such as the reliance on capacitors for energy storage. As a reminder again, capacitors can be over 1,000 times more energy dense than inductors at this scale, so the overall passive component volume and mass are reduced. The FCML converter also generates a frequency multiplication effect such that the volt seconds on the output inductor are greatly reduced, thus improving filter efficiency and size. In this 8-level converter, this corresponds to a reduction on the filter inductor by a factor of 49, which is quite significant. And finally, the losses are spread across many low-profile components, which maximizes the surface area for heat transfer. Overall, this leads to a compact, efficient design. One key consideration for the proper functioning of the FCML converter is startup behavior. When the input is applied to a converter with initially discharged capacitors, as the converter starts switching, the switches may experience excessive voltage stress and get damaged. This is because the initially discharged capacitors have not reached the fractions of the output voltage that they normally do under nominal steady-state operation. The natural balancing behavior of the flying capacitors is characterized by slow time constants, meaning that the charging behavior will not be able to track a fast input ramp or step at startup. In order to tackle this, an additional startup circuit is incorporated in this project to allow the flying capacitors to arrive at their desired levels. Firstly, the output blocking switches ensure that the load is disconnected during startup. And we see that when VLV here is stepped up. Then we turn on the high voltage input blocking switch, which in conjunction with RI provides a roughly constant current to ramp the input to the FCML converter linearly until it hits VLV. The bypass transistor is then turned on to present a low impedance connection to the source. And note that because of RI, a low voltage switch can be used here. And finally, the output switches connect the load to the converter and ramp up the output voltage to the desired kilovolt. Under the scheme, the input and output voltages of the boost converter are gently ramped, allowing the flying capacitors to reach their fractional voltages of the output voltage. We can see that the capacitor voltages VC1 through VC6 are at 1/7, 2/7, and so on of the output voltage, which is at 1,000 volts. This is observed to be true during the input ramp, during the output ramp, and in the steady-state behavior. Combining all of these building blocks, we now come to look at the implementation in a hardware prototype. Pictured first is the top side of the prototype, a view of the bottom side, and finally looking at a side-on. We can look at a few key components in the board, such as the output blocking switches, the onboard digital signal processor, the input blocking switches, the bulk flying capacitors on the backside of the board, and the inductor, which is the tallest component on the circuit. You can see from the side-on view that the inductor is recessed into the board to reduce the overall height of the converter. The power stage is shown here, and it is this section whose volume and mass are used to obtain the power stage only metrics discussed for the converter. We can look at the details of the power stage itself and see the gate driver, the gallium nitride switches, the power and signal isolator, and the inductors, along with the decoupling flying capacitors, which on the top side are mounted to achieve very small commutation loop area. We can now look at the key components used for this prototype, starting with the FCML boost conversion stage. Note here we're using 200-volt gallium nitride switches in this 1,000-volt application enabled by the multi-level topology. The gate drive for these switches is achieved by using isolated gate drivers. We then see the parts for the startup circuit where high voltage silicon carbide switches are used along with isolated gate drive for the blocking switches. And the bypass switch, as previously mentioned, is a low voltage silicon switch in parallel with RI. This is also driven using isolated gate drive circuit. And finally, we note that all of the control logic is implemented on an onboard off-the-shelf TIC 2000 DSP. We can look at the mass breakdown of the board and see that the power stage takes up about half the mass, with the bare PCB itself being the single largest mass contributor. Overall, the prototype weighs in at under 200 grams, which is pretty light for this 10 kilowatt application. And we will look into the power density numbers in a bit. We can look at the efficiency results when we sweep the output power at the input voltage limits, both for the highest battery voltage of 786 volts, as well as the lowest battery voltage at 500 volts. We can see a peak efficiency of 99.1% and 98.9% at the input voltage limits. We can also look at the efficiency as we vary the input voltage, and we see an interesting shape here. The shape is impacted heavily by inductor core losses, which are non-negligible in this work. In the FCML converter, the switch node voltage varies between two levels that would look like this. But as we approach the nominal duty ratios, the inductor ripple starts to approach zero. And this drives the AC losses way down for the inductor itself, and this improves the overall system efficiency. And we see these peaks at the nominal duty ratios for 7th and 5/7, where the ripple approaches zero. We can then compare the results of this work, shown in the far right column, to some other state-of-the-art aircraft DC-DC converters. While all of these converters have different operating ranges, this still identifies the very high performance of this work and demonstrates its excellent power density. As a recap, this work uses an input voltage in the range of 500 to 786 volts, an output voltage of 1,000 volts, 10 kilowatts of peak output, with a peak efficiency of 99.1%, as we just saw, and a very impressive power stage density of 103 kilowatts per kilogram. The other converters pictured here from existing Western literature achieve very high peak efficiencies as well, but all of them are at lower peak power stage densities compared to the work presented here. So then we can look back again at the projections that we started with and compare our results to these. As a reminder, this is what the power stage density projection chart looks like. And here is how this converter's power stage compares. Notably, this far exceeds the aggressive 2050 projection that we had. Of course, when comparing our performance results to the projections, it's also important to keep in mind, it's not just the power stage we care about, but also perhaps the rest of the system itself, which contributes to the system overall aircraft system mass. And if we do that, here is how we stack up when we consider the control, sensing, and startup circuits. This hovers right around that 2050 projection itself, which is very helpful for us to realize that this converter is able to achieve high performance, but there's obviously also scope for further improvement. That same study also contains similar projections for efficiency, which is also an important metric for us to consider, in addition to the power density. And here's how we stack up. We have an aggressive projection, much like with the power density, as well as a conservative projection. And this work in 2026 is well above the projected 2026 efficiency, but still below the 2050 aggressive projection. It is above the conservative projection, which again shows that this work demonstrates excellent performance and identifies that there's scope for greater performance in future work. In conclusion, this work demonstrates the design, optimization, and validation of an 8-level FCML boost converter for electric aircraft power distribution applications. The prototype achieves a peak efficiency of 99.1% and a power stage density of 103 kilowatts per kilogram. This surpasses both projected aerospace targets identified as long-term goals in recent literature, as well as those of other state-of-the-art works in literature. The hardware prototype integrates the necessary embedded controller, as well as circuits for sensing, startup, and output disconnect to demonstrate an integrated solution. Thank you for listening to my presentation. I would also like to take this opportunity to thank the Berkeley Power and Energy Center for supporting my work, as well as the Hearts to Humanity Eternal Foundation Fellowship for also supporting my time as a graduate student at UC Berkeley. Thank you very much.